Okay, we've got this heater thing with a cup of coffee sitting on it, and it heats the coffee through power provided by the laptop it's connected to. Okay, we have to say two factors that affect the rate of temperature transfer to the coffee other than the material of the mug. Okay, so the heater gets all warm here and transfers energy to the coffee. Well, the heater heats the mug and the mug heats the coffee. So the greater the surface area of the contact surface area between the heater and the coffee. So surface area. Also, like I said, it's heating the mug and the mug then heats the coffee. So the thickness of the mug is also a factor. The thicker the mug, the longer it'll take for conduction to transfer the heat from the heater through the mug to the coffee. What else? Of course, temperature of the heater. However hot this thing gets, the hotter the heater gets, the greater the temperature gradient between the heater and the mug, and therefore the greater the rate of energy transfer. I think that's it. Yeah, that's good. That'll do. It's only 2 marks, just 2 of those 3. Okay. B. Explain how energy is conducted through the base of the mug. Right. So we have to explain energy transfer by conduction. So the heater gets hot. This is heating the mug, and the mug then heats the coffee, like we've talked about. So how do you explain or describe conduction? Well, the particles that... Hang on, does it want us to explain energy conducted through the base of the mug? Okay, so we're talking about the base of the mug. The particles, well, how do they get hot in the first place? The heater heats the particles in the base of the mug, and therefore it transfers energy to them. So the particles in the base of the mug, as they gain more energy, they vibrate faster. 1 mark. And when they vibrate, they collide with adjacent molecules in the base of the mug, transferring energy to them and causing them to vibrate. 2 marks. And then the process repeats. Those particles further up in the base of the mug, they're vibrating faster now, so they collide with particles above them and make them vibrate faster. And so energy is transferred through the base of the mug that way. So to get the marks, the concise version is, say that particles vibrate faster as they gain energy, and then use the word collide. They collide with adjacent particles, transferring energy to them, and then the process repeats. They collide with adjacent particles to them, and that's how energy is transferred. Okay. Next, explain how a convection current is set up in the coffee. Okay, so the particles, as we've just described in the mug, are all vibrating fast, so they collide with the coffee particles at the bottom of the liquid, at the bottom of the coffee, and heat them up. So energy is transferred from the base of the mug into the lower layer of coffee by conduction. So the coffee particles in the lower layer vibrate faster because they gain energy. When particles vibrate faster, they spread out. And therefore, as they spread out, the warmer region of coffee becomes less dense. Now, it's a liquid, so you have a region of less dense liquid at the bottom, temporarily, below a region of colder, more dense liquid. And so, the higher energy, hotter region of coffee at the bottom rises above the colder, less dense coffee. And at the same time, the colder, less dense coffee sinks below the warmer. The colder, more dense coffee sinks below the warmer, less dense coffee. And that's convection current. And then the process repeats. The colder, more dense coffee that's sunk to the bottom is now heated by conduction by the base of the coffee mug. Therefore, the particles, as they gain energy, they vibrate faster and become less dense. And therefore, they now rise above, that region of hotter coffee rises above the colder, more dense region above, because the original warm bit has cooled a little bit as it's been sitting up here. And so you've got a convection current. That will get you the 4 marks. So the salient points to get you the 4 marks are: say that the higher energy, faster moving particles at the bottom, say they spread out, use that phrase. And therefore, so that's 1 mark. Therefore, they become less dense, 2 marks. Therefore, you have a region, a hotter region, say that rises above the colder, more dense region, 3 marks. Say the colder, more dense region falls below the hotter region, 4 marks. But always try and do a little bit more than just the bare minimum. And then say the process repeats. This region is now heated and then rises above the original region, which has cooled a bit. And this is a convection current, and the process repeats. Okay, that's the end of the question. I haven't written very much. All right, I just want to say one more thing. The question is over, but this makes me think, well, it's to do with heat, this, isn't it? So you might have heard the expression, heat rises, and you could be forgiven for thinking that that statement is correct, given this question. It's not correct. Heat does not rise, okay? It is correct to say that a warmer region of a liquid or a gas will rise above a colder, more dense region. That is true, okay? But if the phrase heat rises is not true if you're talking about a solid, for example. So if you have, I don't know, an iron bar, okay, and you, let's see, let's turn it into an iron block of some sort, okay? So it's just a lump of iron. If you heat the top, right, then by conduction, in exactly the same way we've described with this question, all the particles at the top vibrate faster and collide with the ones next to them, and heat energy is conducted through the iron to the lower region. In this case, heat is going downwards. So the phrase heat rises is not always true. Yeah, that's pretty much what I wanted to say. It's true that I suppose people say, oh, heat rises because radiators. You know, a radiator gets hot, it heats up the air around it, and it sets up a convection current, just like this. So the warm air around the radiator, okay, you've got your radiator, heats up all the air around it, okay, which becomes less dense. So it rises above the colder air, which then sinks below it, exactly like in the coffee cup. And so it's tempting to think that, to say that heat rises because of radiators, but it's not true. Heat can go sideways as well. If you heated up this side, it would go like that. Yeah. And I don't know if they've got radiators in the International Space Station, but if they do, probably do, they've got to have some form of heat. If this radiator, okay, is in the International Space Station, all the air and the International Space Station and the astronauts, they're all under free fall. Okay. The region of warm air in the International Space Station around that radiator that will not rise. So even in air and water, the phrase heat rises is also not always correct. You need gravity as well in order to pull the more dense air below the hot air. In the International Space Station, the air, the radiator, the astronauts, the space station, it's all under free fall. So there's nothing to pull the less dense, colder air around the radiator underneath. So you've got the colder air all around it. There's nothing to pull that underneath. There's no overall gravitational force because everything is under free fall. Anyway, got quite distracted there, but it's all good stuff. I've said everything's under free fall and I said you need gravity. That's a whole different subject. I will be making videos on the International Space Station gravity. It's very important, a very interesting area. Everything's under free fall in the International Space Station, so there is gravity. It's just that they're constantly falling, but that's a whole new story. See my other videos for that. Right, there you go. Finished. Enough.